You notice it first in the satellite images, there in the kind of details that the ancient builders never expected anyone from the sky to see. There are lines of walls stretching across Peru. There is the base of a temple in Egypt, vast and deliberate. There are the foundations beneath a ruined city in Turkey, stones arranged with intention. And there are the stone circles scattered across Japan, silent and waiting. These places, these structures, they were built by cultures with no shared language. No trade routes connected them. There was no common mythology, no message carried across the oceans. And yet every single one of them carries the same mathematical fingerprint. Every one, as though they were all following a blueprint, a pattern older than any empire that ever rose or fell. It is a fingerprint so precise, so consistent, that it cannot be dismissed as coincidence. It demands explanation. It demands wonder. Modern geometry detection algorithms tools designed originally for robotics, for machine vision, for astrophysics, are now being pointed at these ruins. These algorithms, these mathematical instruments were never meant for archaeology. But when they are turned toward the ancient world, toward the stones and walls and circles left behind, they return with results that are unsettling. The software keeps flagging identical ratios. It keeps finding repeating harmonics. It detects recurring geometric signatures with a kind of impersonal certainty that humans cannot argue with. Golden spirals embedded in floor plans. Vesica piscis patterns hidden in ceremonial platforms. 3 to 4 to 5 triangles determining temple orientations. Hexagonal grids structuring entire city layouts. The numbers keep coming back. The patterns keep repeating. Archaeologists like Alexei Kusenko and Keith Kritso once suspected these patterns. They observed them in fragments, in isolated examples, and wondered. But seeing them confirmed by machine analysis, by the cold logic of algorithms, gives everything a new gravity. The suspicion becomes certainty. The fragments become a coherent whole. And even Kim Malville's work on astronomically aligned sites, work that has been celebrated for decades, begins to look like only one piece of a much larger pattern. His observations about temples aligned to solstices and stellar positions are not wrong. They are incomplete. They are the tip of an iceberg of geometric intention that extends far deeper and far wider than anyone previously imagined. This realization forces an uncomfortable question. How did civilizations, separated by vast oceans, end up building with the same sacred shapes? How did civilizations that rose and fell without ever hearing of each other, without any possibility of communication, without contact of any kind, arrive at the same geometric language? These are not vague resemblances. They are not rough approximations or loose parallels. They are precise. They are measurable. They are intentional. And when you follow these shapes, when you trace those spirals across continents, when you trace those overlapping circles from one side of the world to the other, you begin to sense something beneath the surface, something deeper, some quiet intelligence woven into architecture itself. It is there in every measurement. It is there in every angle. It is there in the proportions that repeat and repeat and repeat. Something every ancient builder seemed to understand instinctively, as though geometry was not merely a tool for construction, not just a practical method for building straight walls and squared corners. As though geometry was something else entirely, a language, a way of encoding ideas, a way of expressing truths that would outlive the empires that carved them, that would outlast the civilizations that built them. You can feel the pull of it now. That same pull that ancient explorers must have felt when they realized that the world was far stranger and far more connected than anyone had imagined. Because if these cultures never shared knowledge, if they had no contact, if there were no trade routes, no migrations, no communication, then the symbols they used must have come from somewhere else entirely. The ratios they honored, the shapes they repeated with such precision, they must have originated somewhere. The question is where? Whatever that somewhere is, you are about to step into it, and the journey begins. Göbekli Tepe and the Threshold. The story of humanity's first builders begins long before recorded history, long before writing, long before metal, long before cities existed. It starts in a place that no one expected, a limestone plateau in southeastern Turkey. The wind is dry there, carrying dust across a field of buried circles. When archaeologists first uncovered these structures, they thought they were looking at a medieval cemetery. It seemed too elegant for the Stone Age, too geometric, too deliberate. But then slowly, as the excavations continued, as more stones were cleared and more measurements were taken, the archaeologists realized what they were actually seeing. Göbekli Tepe, 12,000 years old, older than the pyramids by thousands and thousands of years, older than agriculture, older than everything that came after. It was the first sign that our ancestors had crossed a threshold, a line from which there was no returning, a threshold that we still do not fully understand. Massive stone circles defined with uncanny symmetry, T-shaped pillars arranged in precise formations as though laid out according to an invisible plan. Enclosures that follow subtle mathematical rules, rules that existed long before mathematics had a name. These people were hunter-gatherers. They did not farm. They had no cities. They had no writing. They had no metal tools. Yet the stone circles they built mirror the geometry of civilizations that would come thousands of years later, mirror them exactly, or nearly exactly. Once researchers began measuring every pillar, every alignment, every radius, the geometry revealed itself like a ghost emerging from dust. Slowly, gradually, but with inexorable certainty. Some of the enclosures form nearly perfect circles, impossible to lay out by chance, especially when each is 10 to 20 meters across. Within these circles, pairs of pillars are oriented towards specific points on the horizon, toward points that matter. In 2015, archaeoastronomers analyzing 3D laser scans noticed something peculiar. The alignments were not random. They were not scattered. They cluster around positions of major celestial events. Solstice sunrises, and in some cases, the rising point of visible star groups thousands of years ago. That alone was surprising. But then came the geometric anomalies. When computational archaeologists applied geometry detection algorithms, the hidden structure of Göbekli Tepe began to surface. Several enclosures fit inside perfect circles. The circumference and radius follow the golden ratio, within a margin more precise than anything expected from Stone Age builders. Some pillar pairs form isosceles triangles whose tips aim toward astronomical targets. And most striking of all, a three-point collinearity pattern appears repeatedly. 3 key pillars lying on a perfect straight line. That same straight line, when extended, intersects distant horizons where important star risings occurred in 10,000 BCE. This was not random placement. This was intent. This was memory. This was design. And Göbekli Tepe was not alone in this vision, not alone in this understanding. Across Europe, where the Neolithic world was still young and restless, groups of early builders were shaping landscapes with geometry so subtle that it remained unnoticed for millennia. Unnoticed until modern tools gave us the ability to see what had always been there. On the windswept plains of Brittany, the Karnak alignments stretch across kilometers. Thousands of stones placed in rows so straight that modern surveying equipment struggles to find any deviation. They are almost too perfect, too precise. For decades, researchers dismissed them as ritual markers or territorial boundaries, mere markers of something practical. But then mathematicians began studying their spatial patterns using collinearity analysis software, using algorithms designed to find hidden order. What emerged was a hidden scaffolding. Many lines form exact multiples of 30, 60, or 90 degrees relative to one another. Angles found in hexagonal geometry, angles that should not exist in a Neolithic landscape. Some of the alignments generate triangles with 3 to 4 to 5 proportions. The same right-angle triangle used in Egyptian pyramids thousands of years later. These geometric patterns were not visible from the ground. They were only obvious from above. Yet the builders knew where each stone needed to stand. They understood something about space and proportion that allowed them to achieve this. Further north at the Ring of Brodgar and the stones of Stennis in Orkney, researchers used drone photogrammetry to measure planarity and curvature. What they found shocked even conservative archaeologists. The circles deviate from true circularity by such small margins that only a deliberate mathematical framework could explain them. The outer ring of Brodgar fits a 60-sided circular geometry, essentially a hexagonal system scaled outward into smooth curvature. Again, this was long before writing, long before numbers. But the geometry was already alive. As more sites were scanned, as the data accumulated, a startling picture emerged. Neolithic builders across Europe seemed to share an internalized map of shapes. Circles, alignments, triangles, harmonic ratios, without any contact between regions, without trade, without any visible connection. This is the mystery that begins to announce itself. This is the pattern that starts to demand explanation. The megalithic inheritance. Archaeomathematicians began to suspect a deeper pattern, a pattern that transcended geography, a pattern that transcended time. When those theories were compared with data from Göbekli Tepe, something clicked. The same geometric habits existed thousands of years earlier, thousands of miles away. This was not a later invention. It was not something that someone in Europe had invented independently from Turkey. It was a continuation of an older memory, a persistence of knowledge, a transmission through time itself. And then came the megalithic sites with dimensions tied to the golden ratio, to that mysterious proportion that would fascinate philosophers and mathematicians for millennia. At Newgrange in Ireland, a passage tomb older than Stonehenge, the ratio of the chamber width to the height of its corbelled dome closely approximates the golden ratio. Not approximately, closely. Within a margin that suggests intention rather than accident. Its entrance stone contains spirals carved with a precision that suggests more than artistry, more than mere decoration. Some of those spirals follow logarithmic curves, tightening inward in smooth mathematical spirals. Spirals that seem to follow a rule that no one had written down, a rule that no one had taught, a rule that somehow had been transmitted into the hands and eyes of the builders. In 2020, a team using curve-fitting software showed that several megalithic spirals align within 1 to 3% of a true golden spiral, a margin of error comparable to Bronze Age metalwork, not Neolithic stone carving, not stone carving from 12,000 years ago. This precision is astonishing. It demands explanation. Across the sea in Malta, the temples of Hagar-Chim and Menajdra present yet another mystery. They have ellipsoidal plans that archaeologists once called oddly organic, as though the builders were following some intuitive sense of form rather than geometric logic. But when mathematicians analyzed their floor plans, they discovered that the ellipses correspond to specific ratios between major and minor axes, ratios that appear again in later Mediterranean architecture, ratios that were not invented in Malta. They were discovered there. They existed in the geometry of the world, waiting to be found. Menajdra temple, in particular, contains an internal division whose proportions map almost exactly to 1 to the square root of 3, a ratio foundational to later hexagonal geometry, a ratio that would not be formally understood for thousands of years, a ratio that the builders of Menajdra somehow knew, somehow encoded in stone, somehow transmitted through their fingers and vision to the future. These builders were not merely placing stones in a haphazard way. They were shaping space according to patterns that resonate across civilizations, and each discovery only sharpened the paradox, the fundamental paradox that haunts this entire investigation. As the millennia unfolded, as time moved forward, as one civilization rose and another fell later, cultures inherited these geometric ideas, or expanded them, or reinvented them, but they did not create them. They stepped into a stream that already had momentum, a current of mathematical imagination originating somewhere deep in prehistory, deep in the past, in a place and time that we can barely see, much less understand. That current would continue to flow. That inheritance would continue to be passed down, and in each new civilization, it would find new expression, new application, new meaning. Egypt and the language of proportion. Egypt provides one of the clearest examples of this inheritance. By the time the Old Kingdom rose, around 600 BCE, geometry was no longer intuitive. It was explicit, taught, codified. Scribal schools trained rope stretchers in how to create perfect 3 to 4 to 5 triangles. Architects used Sekhet's slope ratios to define pyramid angles with precision. This was not guesswork. This was system. But several pyramid dimensions reveal something older, something that predates the explicit teaching, something that suggests the Egyptians had inherited an understanding from even more ancient times. The golden ratio appears again and again in pyramid design, not by coincidence, but by deliberate design, by intentional choice. The Great Pyramid's half-base to height ratio closely approximates the golden ratio. The bent pyramid's change of angle corresponds to geometric harmonics. Even the alignment to true north is so precise that it suggests a long tradition of astronomical geometry stretching back before the pyramids were ever built. But Egypt was not the origin. It was an inheritor of something much older. And the same principle echoes in the earliest cultures of the Indus Valley, where uniform grid plans appear in cities like Mohenjo-Daro and Harappa. Archaeologists discovered that city blocks follow a recurring ratio, 1 to the square root of 3. Again, that ratio. Again, the same geometric principle, linking to hexagonal geometry across continents, across thousands of years. Standardized bricks were made in precise 1 to 2 to 4 proportions. Drainage channels align according to reciprocal angles. Even early seals contain mandala-like patterns structured on nested circles. The geometric consciousness was everywhere. It was in every practical decision. It was embedded in every measurement. In China, the Neolithic Liangzhu culture built jade discs with perfect circularity long before bronze tools existed, long before the technology existed that would make such perfection easy. Yet the builders achieved it. Their ritual axes often contain hidden 3 to 4 to 5 triangles. The same triangle. Again, the same proportion appearing in different contexts thousands of miles away. And when laser scanning was applied to Liangzhu levees and waterworks, researchers found geometric planning embedded in the hydraulic layout. Water management following geometric rules. Practical necessity guided by mathematical proportion. Across the Pacific, in ancient Japan, the Asuka alignment and Kofun burial mounds follow axial geometries whose angles mirror those in Western megalithic sites, despite complete cultural isolation. No contact, no trade, no communication, no way for knowledge to have traveled. Yet the angles match, the proportions align. The geometric consciousness emerges independently, yet consistently. This is not coincidence. This cannot be coincidence. This is something deeper, something more profound, something that suggests a shared source. Someone somewhere charting the dawn of civilization had already learned to see the world as a series of relationships, circles, alignments, ratios, harmonics. And that vision spread not by conquest, not by trade, not by writing, but by human memory carried across generations, by intuition passed down through time, by a way of seeing the world that somehow persisted even as cultures rose and fell around it. Computation reveals the hidden signature. The more archaeologists scanned, measured, and compared, the more the similarities piled up. But the turning point came when computational geometry entered the field. Programs originally created for robotics, designed to detect edges, curves, and symmetries, were repurposed for archaeology. When researchers fed satellite imagery and three-dimensional scans of ruins into these algorithms, the software detected repeating motifs with clinical impersonality. It did not care about cultural boundaries. It did not care about languages or chronology. It did not care about our assumptions about how knowledge travels and how civilization develops. It simply saw patterns. And what it saw looked like the world's oldest architectural signature, a signature written in geometry, a signature that appeared again and again no matter where the software looked. Circles subdivided into 60 segments, triangles locked into 3 to 4 to 5 proportions, spirals following the golden ratio, collinear rows pointing to solar or stellar points, ellipses whose axes followed geometric series, ratios that reappeared not once, but thousands of times. In every region, in every period, in every culture that had the knowledge to build monuments. From Göbekli Tepe's hunter-gatherers to Egypt's pharaohs, from Orkney's stone circles to the Indus Valley's grids, from ancient Mesoamerica to China's imperial cities. The same shapes waited beneath dust and soil. The same proportions had been encoded in stone. The same language had been spoken across time and space. This was humanity crossing the threshold. The moment the world shifted from survival to imagination. When the ancestors who once followed herds began to follow patterns. When stones became symbols. When geometry stopped being something embedded in nature and began to be something that humans could embed into nature consciously, deliberately, intentionally. This was the moment when the game changed. And quietly in the margins of this ancient story, later civilizations would inherit and refine these ideas. Islamic astronomers and Persian architects and geographers would take the spirals and turn them into cosmograms. They would take the triangles and turn them into star maps. They would take the circles and turn them into sacred diagrams. Their moment will come later in the journey. But the roots are already here, planted deep in forgotten soil, in stone older than empires. The deeper researchers dig, the more one question presses against the mind with increasing urgency. Was this geometry invented by scattered tribes, emerging independently, again and again, sparks across the dark? Or was it remembered, echoes of a much older understanding, carried through time before the first stones were ever raised? The ruins do not answer, but their symmetry suggests something profound. Humanity did not stumble into mathematics. It stepped across a boundary into a world where shapes held meaning, where numbers were not abstractions, but truths written into the bones of the earth. And someone thousands of years before history began was already reading them, already understanding them, already building with them in mind. The Egyptian mastery and the sacred triangle. Long before the Mediterranean glistened with the scattered civilizations of Greece and Rome, long before the vast empires of Mesopotamia fully realized the mathematics hidden in their ziggurats and temples, Egypt rose along the banks of the Nile, a river that shaped life with quiet inevitability. That shaped commerce. That shaped thought. It was a land that demanded precision. The Nile flooded predictably each year, depositing fertile silt across the desert floor. But the river's rhythms also created a challenge. The land shifted, boundaries blurred. The flat plains could betray the careless surveyor. It was here that geometry first became not merely a tool, but a sacred instrument, a language through which humans could impose order on chaos. The Egyptians were masters of observation, not only of the heavens and the river, but of the very earth beneath their feet. And when they began building monuments intended to last through eternity, that observational skill crystallized into mathematics, into geometry, into proportion. It is impossible to study the pyramids without noticing that they are far more than tombs. They are calculations rendered in stone, architectural symphonies of proportion alignment and scale. The Great Pyramid of Giza, Khufu's masterpiece, exemplifies this perfection. Surveyors and archaeologists, including Mark Lehner and Glenn Dash, have spent decades meticulously recording the base and height of the pyramids, comparing measurements, comparing angles, comparing relationships between the stones. Their research confirms that the Great Pyramid's dimensions are not arbitrary. They were chosen deliberately. The ratio of the half base to the height approximates the golden ratio, that same proportion that appears in Malta and Japan in the Indus Valley. A mathematical relationship that would captivate Greek philosophers centuries later. Whether the builders understood it consciously as a ratio or as a proportion derived from practice remains debated. But the precision is undeniable. The limestone casing stones, some polished to reflect sunlight, were cut and laid to form near-perfect angles with errors so small they challenge modern surveyors. The 3 to 4 to 5 triangle emerges here as the most elegant and practical of tools. Known in ancient Egypt as the sikt, it allowed builders to establish right angles with ropes marked into 3, 4, and 5 units. By stretching the rope across the ground and measuring the diagonal, they could create a perfectly square base for a pyramid or temple. This simple principle is nothing less than applied trigonometry centuries before formal trigonometric tables existed. Jean-Philippe Lauer and others have shown that the careful use of these triangles enabled the construction of pyramids, mortuary temples, and causeways aligned not just to each other, but to points on the horizon with astronomical significance. Every alignment was intentional. Every angle served a purpose. Nothing was left to chance. The orientation of the Great Pyramid to true north, accurate within a fraction of a degree, suggests that this was no accident. Surveyors use stars, particularly the circumpolar stars, as guides translating celestial observation into terrestrial geometry. The Nile itself shaped these constructions. Every year, as the river rose and fell, land boundaries shifted. Egyptian surveyors measured plots with taut ropes, ensuring that temples and tombs maintained proper alignment and proportion, despite environmental changes. The land itself became a canvas for mathematical imagination. The genius of Egyptian geometry is not limited to triangles and linear measurements. Circular forms appear in temple designs, sunken courts, and mortuary enclosures, often in proportions echoing the golden ratio. The pyramid's base, when doubled and compared with the perimeter, reveals a subtle harmonic relationship. A relationship that seems to anticipate the logarithmic spirals found in nature, in shells, in galaxies, in the growth of living things. Researchers employing photogrammetry discovered that the spacing between shafts and chambers often corresponds to proportions that repeat in smaller and larger scales. A fractal-like sensibility embedded long before fractals were formally conceived. A self-similarity at different scales. This is not accident. This is knowledge. The Mesopotamian cosmos and the sacred number. After the rivers of Mesopotamia carved their fertile plains, and long before the vast empires of Mesopotamia fully realized the mathematics hidden in their structures, human thought began to turn inward. But in Mesopotamia, in the land between the Tigris and Euphrates, that turning inward took a distinctive form. Here, humans began to codify time and space, not merely as practical measures, but as reflections of cosmic order. Babylon and Nippur became the laboratories of the first mathematicians, astronomers, and architects. A civilization where calculation and observation were inseparable, where mathematics was sacred, where numbers carried meaning beyond mere quantity. Mesopotamia was a land of layered complexity. The rivers dictated life flooding unpredictably and reshaping the earth. Yet in this chaos, humans sought order in the heavens. Babylonian scholars developed a numerical system based on 60 a decimal system that would shape mathematics, timekeeping, and eventually the geometry of the universe itself. Unlike the base 10 systems familiar today, base 60 allowed unprecedented flexibility in expressing fractions and ratios. It enabled them to model planetary motion with surprising precision. Every circle was divided into 60 parts, every hour into 60 minutes, every minute into 60 seconds. In a sense, the number 60 became a bridge between the terrestrial and the celestial. It became a language capable of expressing both the practical and the cosmic. It is within this framework that architecture, mathematics, and cosmology began to converge. The ziggurat stepped pyramids rising above city landscapes were not merely temples, they were physical manifestations of layered cosmologies, microcosms of the heavens themselves. Each level represented a plane of existence, each ascent a movement closer to the divine. Scholars such as Stephanie Dalley and Paul Collins have analyzed the alignment and proportions of ziggurats, showing that their dimensions often correspond to astronomical intervals. The rising and setting of stars, the lunar cycle, the paths of planets visible to the naked eye. The geometry was precise. The intention was clear. Vesica Piscis forms those overlapping circles revered across millennia appear repeatedly in Mesopotamian temple layouts. In some Sumerian precincts, twin enclosures trace elliptical or vesica-like shapes, their axes aligned with solstitial points on the horizon. Modern archaeologists, using satellite mapping and LiDAR technology, have confirmed these orientations with remarkable accuracy. The precision is striking. These geometric forms were not aesthetic afterthoughts. They encoded celestial knowledge, a dialogue between earthly structures and cosmic patterns. Among the most astonishing relics of this civilization are the clay tablets, the artifacts of human thought baked into permanence. Plimpton 322. A tablet from approximately 1800 BCE contains a table of numbers that mathematicians now recognize as Proto-Pythagorean triples. Rows of numbers correspond to the sides of right triangles, demonstrating an understanding of geometric principles centuries before Pythagoras himself was born. Researchers such as Eleanor Robson have painstakingly analyzed these tablets, showing that Babylonian scribes were capable of manipulating complex ratios, solving problems of distance and angle for architecture, land division, and astronomy. The connection between numbers and the sky was explicit. Planetary cycles, Venus, Mars, Jupiter, Saturn, were recorded with geometric proportions. Their periods encoded in tables that could be applied to both ritual timing and practical governance. When modern software simulates these cycles using Babylonian ratios, the correlation with observed astronomical events is striking. For example, Venus's synodic cycle, approximated as 584 days, aligns with divisions of ziggurat steps. Lunar eclipses and solstices are often encoded in the layout of temple courtyards. Geometry here was a lens through which humans could model time and anticipate the rhythm of the cosmos. The intellectual ripples from Mesopotamia would eventually reach far beyond its cities. Greek philosophers traveling to Babylon or reading translations inherited the base 60 fractions, the triangular knowledge, the harmonic ratios. Thales and Pythagoras drew upon these ideas, developing the theorems and abstractions that form the core of classical geometry. Later, Islamic scholars in Baghdad, particularly during the House of Wisdom in the 9th and 10th centuries, codified Babylonian astronomical observations, refining them into trigonometric tables and cosmographic maps. Here again, the geometry of the heavens influenced human architecture, now in mosques and observatories, mirroring patterns first recorded on clay tablets. The layout of ziggurats carries echoes of these ratios. Archaeologists using photogrammetry and digital reconstruction software have found that the step heights and platform widths correspond with sequences derived from base 60 calculations. The great ziggurats rise in measured proportions that approximate harmonic triangles. When viewed from above, the stepped terraces form concentric geometric layers, almost like rings echoing outward from the sacred core, repeating the patterns of spheres and ellipses that chart the motion of celestial bodies. These forms seem to encode knowledge of both the earth and sky, Greece and the abstraction of eternity. After the rivers of Mesopotamia carved their fertile plains and the Nile sculpted its endless horizon, human thought began to turn inward in a new way. Greece emerged as the first civilization to treat geometry not merely as a tool of builders, priests, or astronomers, but as a philosophy, a lens through which the cosmos itself could be interpreted. Here mathematics became an instrument of thought, a dialogue between the mind and the structure of reality. And the human imagination stepped fully onto the stage of abstraction. The figure of Pythagoras looms large over this transformation. Born on the island of Samos around 570 BCE, he traveled extensively, likely to Egypt, Babylon, and possibly even farther east. He absorbed knowledge that would be reinterpreted through Greek reasoning. Pythagoras is often credited with formalizing the relationships between numbers and shapes. Yet what he and his followers produced was far more than theorems. It was a vision of the universe as a living, harmonious system, a cosmos in which mathematics was both music and structure. Numbers were not mere counters, but the essence of being. And shapes were the visible manifestation of numerical harmony. The Pythagorean school believed that everything in existence could be expressed through ratios, proportions, and geometrical forms. It was in this intellectual atmosphere that the first Platonic solids were conceptualized. The tetrahedron cube, octahedron, dodecahedron, icosahedron, 5 perfect forms, 5 expressions of universal order. Plato, a student of Socrates, and a philosopher deeply concerned with the nature of reality, later codified these solids in his dialogues, connecting them to the elements, fire, earth, air, water, and the cosmos itself. These forms were not arbitrary. They were the geometry of existence, the skeleton of creation. The tetrahedron, with its sharp triangular faces, embodied the dynamism of fire. The cube embodied the stability and permanence of Earth. The universe, it seemed, was structured according to mathematical law, a law written in geometry, a law that could be read and understood by the human mind. Abstract geometry in Greece did not emerge in a vacuum. Egyptian and Mesopotamian mathematics, absorbed through travel trade and observation, provided a foundation. The right-angled triangles of Egypt, the sexagesimal ratios of Babylon, the observational precision of their temples and ziggurats. All of this informed Greek thought, even if only as inspiration rather than direct replication. Greek mathematicians distilled these practical applications into theoretical frameworks. Euclid, working in Alexandria centuries later, would codify these principles into the elements, creating a system that combined logic deduction and spatial reasoning in a way the ancient world had never seen. Within the Hellenic world, geometry became a mirror of both nature and mind. The Greeks observed spirals in shells, the branching of trees, the arrangement of petals, and noted the ratios inherent in these forms. The golden ratio, already encoded into Egyptian monuments and possibly even earlier Neolithic structures, was now recognized as a principle of harmony and proportion, a bridge between natural forms and human understanding. Architects, sculptors, and city planners began to embed these ratios into temples, theaters, and public spaces, translating abstract thought into tangible experience. The Parthenon in Athens, constructed in the 5th century BCE, exemplifies this approach. Its facade columns and spacing embody ratios that approximate the golden ratio, producing a sense of harmony and visual balance that seems to transcend mere mathematics. Even the curvature of the stylobate, the platform on which columns stand, was adjusted to counter optical illusions, demonstrating a sophisticated understanding of perception, proportion, and geometry. Here, mathematics, art, and philosophy converge. The implications ripple outward through centuries. Greek geometry also introduced rigorous proof, establishing a method for validating relationships between shapes and numbers. Unlike the practical geometry of Egypt or the observational tables of Babylon, Greek mathematics demanded logical certainty. Euclid's postulates provided a foundation upon which future civilizations could build, extending from architecture to astronomy to theoretical physics. This system of reasoning transformed geometry into a universal language, one that could travel across space and time, independent of culture, language, or geography. And yet, as powerful as Greek abstraction was, it remained rooted in observation. Plato and the Pythagoreans did not float in a vacuum of pure theory. They observed the world and the heavens, noting recurring proportions, symmetries, and patterns. They codified and idealized what earlier civilizations had discovered practically. In doing so, they created a bridge between applied geometry used by Egyptians, Mesopotamians, and Neolithic builders, and a philosophical framework that would inform every subsequent civilization interested in cosmic order. The East responds. India, China, and convergence. Far to the east, in lands separated from the Mediterranean by mountains, deserts, and vast distances, human thought was following a parallel path. The sacred geometries of the East developed independently, yet with a striking resonance to what was happening in Egypt, Mesopotamia, and Greece. In India, geometry was inseparable from spirituality. The earliest sacred diagrams, mandalas, served as cosmic maps, visualizations of the universe itself. These were not mere artistic patterns created for decoration or beauty. They encoded philosophical principles. They encoded astronomical observations. They encoded mathematical precision. Mandalas often consist of concentric circles, squares, and nested triangles, each layer representing a plane of existence or a stage of consciousness. Scholars such as Sarvepalli Radhakrishnan and modern researchers in archaeomathematics have shown that the construction of mandalas follows precise ratios, sometimes approximating the golden ratio and exhibiting radial symmetry that mirrors celestial motion. When a devotee meditates upon a mandala, they are not only contemplating divinity, they are engaging with a mathematically structured cosmos, a dialogue between human perception and universal order. The Sri Yantra, perhaps the most sophisticated of these geometric constructs, is composed of 9 interlocking triangles, creating 43 smaller triangles in a precise pattern. It is a visual representation of the cosmos, a map of the energy forces that govern both matter and consciousness. Recent studies using digital reconstruction have demonstrated that the angles and intersections within the Sri Yantra correspond to ratios that approximate the golden ratio, creating a dynamic interplay of symmetry and proportion. Constructed on temple floors or etched into sacred diagrams, it served as both a spiritual tool and a blueprint for cosmic harmony. Here, geometry is not abstract. It is experiential, meditative, alive, a means to align human activity with the larger rhythms of the universe. Vastu Shastra, the ancient Indian system of architecture, further codified geometry into lived space. Its principles dictate orientation proportions and layout based on cosmic laws, ensuring that buildings harmonize with the natural and celestial order. Temples, homes, and city plans were designed according to these laws, creating a spatial order that reflects both aesthetic and metaphysical concerns. Researchers in cultural archaeology have noted that ancient cities, such as Mohenjo-Daro and later urban developments in South India, exhibit vastu-aligned grids. Streets, courtyards, and sacred spaces follow proportional relationships derived from simple ratios, triangles, and squares. Here again, we see geometry emerging as a universal language, one that unites practical architecture with philosophical insight. Far to the north and east in China, geometry found expression in entirely different yet equally sophisticated forms. Bronze vessels of the Shang and Zhou dynasties display hexagonal patterns, suggesting an early understanding of tessellation and symmetry. These patterns were not mere decoration. They encoded ritual. They encoded cosmology. They encoded social hierarchy. The hexagon, with its inherent efficiency and tessellating ability, may have also been a mathematical insight applied to both material and conceptual structures. Archaeologists and material scientists studying Tang and Hanamara artifacts have identified ratios and proportions that hint at phi relationships, suggesting that ancient Chinese artisans were sensitive to harmonic proportions long before they were formally described in the West. The Forbidden City completed during the Ming Dynasty is perhaps the most iconic demonstration of cosmological grid planning in China. Its vast complex, with a perfect axial symmetry stretching over 7 square kilometers, reflects principles of balance and order derived from both astronomy and philosophy. Researchers in architectural history have shown that the placement of gates, halls, and courtyards follows precise modular ratios, echoing the cardinal points and aligning with celestial bodies. Even the orientation of the Hall of Supreme Harmony aligns with solstitial sunrises, embedding cosmic rhythms into urban space. Mathematics, in this case, is inseparable from ritual and governance. It is geometry in service of cosmic, social, and political harmony. The I Ching. The ancient Book of Changes encodes binary patterns that map onto hexagons, 64 line symbols representing cosmic processes. Scholars have noted that the underlying mathematics of the I Ching, combining symmetry, inversion, and reflection, is inherently geometric, demonstrating an early grasp of combinatorial structures and duality. In effect, these are algorithms of balance and transformation, translating abstract cosmic principles into tangible symbolic forms. When we compare India and China, we see distinct cosmologies, yet a convergence in their geometric understanding. Triangles, circles, grids, ratios, recur across thousands of miles separated by mountains, deserts, and oceans. In both regions, sacred structures are aligned to celestial events. Proportional grids govern urban layouts. Symbolic patterns encode philosophical and astronomical knowledge. The geometry may manifest differently. The Sri Yantra in India, the hexagonal tessellations in China. But the underlying principle is the same. The universe can be understood and expressed through form ratio and symmetry. The America's mirror, empires of the West. Long before European explorers crossed the Atlantic, civilizations in the Americas had already begun charting the cosmos, encoding its rhythms in stone, earth, and sky. These societies, separated by oceans from Eurasia for millennia, developed intricate systems of knowledge that astonishingly mirror geometric principles found in Africa, the Near East, and Asia. Triangles, spirals, ratios, cosmic grids. They appear again not through transmission or trade, but through independent observation, intuition, and invention. The Americas, it seems, held their own sacred code written in geometry. In the lands of Mesoamerica, the Maya civilization flourished, leaving behind cities' temples and calendars that reflect extraordinary mathematical sophistication. Maya astronomers observed the sun, moon, Venus, and other planets with incredible precision, recording cycles in codices, inscriptions, and monumental architecture. Anthony Aveni, a leading archaeoastronomer, has shown that Maya temples and observatories are aligned to celestial events. Solstices, equinoxes, and the movements of Venus, with a precision rivaling contemporary Old World civilizations. The pyramid temples at Uxmal and Köpen follow precise angular relationships, creating terraces and platforms that encode solar geometry. The Maya also developed mandala-like cosmograms, circular or square arrangements of sacred spaces that reflect cosmic order. Linda Scale, one of the foremost experts on Maya iconography, emphasized that these layouts were not mere decoration. They were maps of the universe connecting human activity to celestial cycles. Circles, radial axes, nested triangles appear repeatedly, suggesting a deep understanding of geometric relationships. Some researchers note that the ratios embedded in these structures, including the heights of pyramids relative to their base dimensions, approximate the golden ratio. A striking parallel to Egypt, Mesopotamia, and Greece. Far to the north, in the Valley of Mexico, Teotihuacan rose as one of the most meticulously planned cities in pre-Columbian history. Its main avenues, pyramids, and plazas follow precise axial alignments that correspond to solar risings and settings. The Pyramid of the Sun, one of the largest in the Americas, sits on an axis slightly offset from true north, aligned instead with the point of the sun on certain ritual dates. Archaeologists have noted that the placement of pyramids, residential compounds, and ceremonial spaces repeatedly employs triangular and modular divisions, creating a geometric network across the city. Research in archaeoastronomy, particularly by Clive Ruggles, demonstrates that Teotihuacan's planners applied consistent geometric ratios in the orientation of streets, plazas, and pyramids, reflecting an understanding of the interplay between earth and sky. Moving westward into the Andes, the Inca civilization presents yet another astonishing application of geometry. Inca architects, without the use of mortar, constructed polygonal walls with astonishing precision, Stones fit together so perfectly that even a knife blade cannot be inserted between them. Scholars such as John H. Rowe and Terence N. Daltroy have documented that these polygonal walls often employ geometric angles that create stability and harmony, effectively combining structural necessity with aesthetic proportionality. At Machu Picchu, the terraces, temples, and residences follow patterns that mirror the contours of the landscape. Yet within those contours, ratios appear that echo the principles seen in other distant civilizations. Triangles, proportional divisions, orientation aligned with solstices. Even temple terraces from Ollantaytambo to Sacsayhuaman reveal phi-like ratios in their step heights and horizontal dimensions. Researchers employing photogrammetry and three-dimensional modeling have demonstrated that the Inca were consciously creating harmonious ratios likely derived from observation of natural forms and celestial events. Solar alignment was a key factor. Windows, doorways, and platforms correspond to sunrises on solstices and equinoxes, ensuring that sacred architecture resonated with cosmic rhythms. The repeated appearance of these ratios across structures, separated by hundreds of kilometers, suggests a coherent geometric tradition embedded in the collective understanding of the Inca people. The question arises with urgency and force. How did these principles emerge in complete isolation from Eurasian civilizations? While the Americas were separated by vast oceans, the recurrence of golden ratios, triangular grids, and cosmological alignments implies a universality to geometric thinking. Are these ratios simply the most efficient way to stabilize structures and orient them to the sun and stars? Or is there something deeper? A cognitive or natural imperative that guides humans towards certain geometric forms when attempting to reconcile architecture with the cosmos. Technology unveils the ancient code. Beneath the surface of ancient monuments, hidden in plain sight, lies a lattice of proportion and symmetry that only now, with modern tools, can be revealed. For centuries, the stones of Angkor Wat Borobudur, Petra, the desert cities of the Middle East, and the great monuments of Egypt seemed mute in their perfection. Their geometry was admired, but partial. It took the 21st century to unlock the geometries they had encoded, not by chisels, but with light particles, data, and algorithms. In 2012, a turning point arrived. Archaeologists, long frustrated by jungle canopy hiding the ruins of the Khmer Empire, secured airborne access. A helicopter flying over central Cambodia, scanning the terrain with LiDAR. Over days, the machine fired millions of laser pulses. When the data returned, researchers found not fragments of monuments, but an entire city. Dozens of temples, reservoirs, causeways, embankments, and habitation zones across some 300 square kilometers stood revealed. Structures invisible to explorers on foot or from the ground. This was the first truly large-scale archaeological LiDAR survey in Asia. Its revelations forced a dramatic reinterpretation of the scale, ambition, and planning of the Khmer Empire. No longer a collection of isolated temples, Angkor appeared as a planned urban complex where geometry shaped not just pyramids, but rivers, cities, waterworks, and human lives. These LiDAR maps provided the terrain. But to read the hidden geometry, the alignments, ratios, spirals, modular grids, archaeologists turned to photogrammetry and three-dimensional reconstruction. Drone flights captured temple complexes from multiple angles. Ground surveys recorded the layout of stones, foundations, and causeways. At Southeast Asian sites, but also in other regions, researchers began building digital models. Geometric skeletons of lost cities. These models revealed proportional relations not obvious in the field. Terraces arranged in radial modules. Platforms subdivided into nested rectangles. Causeways aligned along axes corresponding to solar or lunar paths. Repeating modules that echoed harmonic subdivisions. These are relationships of 1 to 2, 2 to 3, 3 to 4, even approximations of the golden ratio. As these data sets multiplied, a new tool entered the archaeologist's toolbox: machine learning and pattern recognition. In 2023, a paper titled Archaeological Sites Detection with a Human-AI Collaboration Workflow described how deep learning models originally developed for urban planning and remote sensing could be adapted to detect buried structures in landscapes. By running semantic segmentation on satellite and aerial imagery, the algorithm flagged potential archaeological features: enclosures, walls, avenues, which human experts then verified on the ground. The system achieved detection accuracy near 80%, transforming months of fieldwork into weeks of scanning. But beyond simply spotting ruins, more advanced workflows began to analyze geometry itself. Using three-dimensional reconstructions from LiDAR and photogrammetry, researchers developed software capable of extracting angles, alignments, and proportions, automatically scanning entire temple complexes for spirals, right triangles, rectangular grids, and nested modules. When fed data from Angkor Petra and other sites, the algorithms returned a startling pattern. Many structures across unrelated cultures employed similar geometric templates: rectangular galleries split by right angles, temples arranged around central squares, adaptations of circle-square layouts, repeated proportional relationships echoing simple harmonic divisions. In parallel, particle physics entered the field of archaeology. In December 2015, a team led by physicist Kunihiro Morishima at Nagoya University placed muon detectors inside the Queen's Chamber of the Great Pyramid of Giza. Built circa 2560 BCE under Pharaoh Khufu. Muons are subatomic particles born when cosmic rays strike Earth's atmosphere. They pass through rock, but their absorption varies with material density. By measuring muon flux from multiple directions, scientists reconstruct a density map where muons pass more freely. There must be voids. In March 2016, after months of data collection, the first anomalies appeared. From 2016 to 2017, two further independent detection methods confirmed the findings. Scintillator hodoscopes from Japan's KEK and gas detectors from France's CEA all confirmed the anomaly. In November 2017, the team announced the discovery of a large, previously unknown cavity above the Grand Gallery, the so-called Big Void, at least 30 meters long with a cross-section comparable to the Grand Gallery itself. It was the first major internal structure discovered in the pyramid since the 19th century. This was not a subtle crack. It was a large volumetric anomaly invisible to the naked eye, undetectable by traditional archaeology, but laid bare by muon radiography. It transformed the Great Pyramid from a solid monolith to a structure with hidden chambers, potentially part of an internal architectural geometry long lost to history. The combination of modern technologies, LiDAR mapping, photogrammetric reconstruction, AI geometry detection, muon tomography, creates a powerful new paradigm. No longer must archaeologists rely solely on fragments, ruins, and the vestiges of history. They can reconstruct entire cities. Overlay internal and external geometry. Analyze global patterns statistically. This is a transformation in how we understand the ancient world. This is a new way of reading the stones. The universal thread and the final question. Across the world, across time and space, across deserts, oceans, and mountains, humanity has repeatedly returned to the same geometric forms. Circles, triangles, spirals, hexagons. They recur in Egyptian temples, Hindu mandalas, Greek spheres, Chinese cosmograms, and Islamic mosques. Civilization after civilization separated by millennia and cultural chasms arrived independently at the same language of proportion. It is as though geometry itself whispers across history. A universal code waiting to be read. A bridge between human perception and the cosmic order. The myths of ancient peoples speak in parallel motifs. The Egyptian creation egg, cradling the birth of the cosmos, mirrors the Hindu lotus unfolding its petals to reveal the universe within. Greek philosophers envisioned the perfection of the cosmos as spherical, a unity of heaven and earth. Chinese cosmograms depict the heavens as a circle, the earth as a square. The same interplay of symmetry echoed in Islamic architecture, where unity is expressed as a balance of proportion and repetition. Across these worlds, geometry becomes more than measurement. It becomes metaphor theology and philosophy. The shapes themselves are statements, bridges between what is seen and what is eternal. In this way, humanity, through its architects, artists, and surveyors, has learned to navigate both worlds, the tangible earthly realm and the celestial universal realm. Each monument, each sacred layout, each tessellated tile represents a step along the hero's journey. A crossing from simple survival into mastery of abstraction, observation, and cosmic understanding. We are the inheritors of a vast geometric consciousness, transmitted not through language, but through proportion, angle, and pattern. And yet the question remains pressing, an insistent, demanding answer. If this language is universal, where did it originate? Did human minds invent these forms independently, guided by perception and necessity? Or did they tap into principles already written into the fabric of the universe? The consistency of ratios, the recurrence of the golden spiral, the precise alignment with solstices, the fractal repetitions across continents suggest a deeper order, a template embedded in reality itself. Geometry may not merely be a human creation. It may be the universe expressing itself through the medium of human hands and minds. If every empire built the same shapes, if spirals, triangles, circles, and hexagons recur across continents and centuries, the final question remains. Were we building monuments to ourselves, asserting our place in the cosmos? Or were we in some profound sense building monuments to the hidden architecture of reality itself? And perhaps in that act, humanity glimpsed for the first time the sublime truth that the universe in its infinite complexity had been whispering its patterns all along. And we, through stone and proportion, finally learned to listen. The sacred geometry that appears in temples and plazas, in mansions and mosques, in spirals, carved in stone and grids laid across the earth, speaks a language older than words. It speaks of a vision, a seeing, a recognition that the cosmos is not chaos, but order, not randomness, but pattern, not silence, but song. The ancient builders heard it. They heard it in the motion of the stars. They heard it in the growth of shells. They heard it in the proportions of the human body. They heard it and they built. They built to honor what they had heard. They built to make it visible. They built to teach those who would come after. And now at last, with our machines and our measurements, with our algorithms and our understanding, we are beginning to hear what they heard. We are beginning to see what they saw. We are beginning to understand that geometry is not merely a tool. It is not merely an ornament. It is a language. The language of creation itself, spoken first in the stars, spoken in the structure of atoms, spoken in the spirals of galaxies and the curves of shells, and heard by ancient minds who with stone and rope and vision translated that cosmic language into form, into structure, into monuments that would endure, that would speak, that would wait for us to finally understand. The journey continues, the patterns remain, and the eternal question echoes across millennia. What is geometry telling us? What are the stones trying to say?